Hello everyone, my name is Shaza and I'll be taking you through question 1. So our main goal here was to see how we can recover digital evidence that has been deleted. So for this task we used Autopsy. It's a famous open source forensic tool. Basically, we wanted to simulate a real investigation, so we deliberately deleted some files from a USB drive. And then we used Autopsy to dig into the unallocated space to find them, extract the metadata, and make sure the data wasn't corrupted. So it's all about proving that deleted doesn't always mean that it's gone forever. So before the recovery, we had to create the crime scene. So I used a standard USB drive and saved two specific files. One is a Word document and the other one is a PNG image file. So before I deleted them, I made sure to capture the original metadata such as the exact file sizes and timestamps because this is our baseline. After that, I performed a shift delete. This is different from just dragging files to the trash. This bypasses the recycle bin entirely. So as you can see in the bottom screenshot, the file explorer shows the drive is empty. So now it's ready for the forensic part. Next, I loaded the drive into Autopsy. So I created a new forensic case and ran what we call ingest modules. So I specifically selected things like for recovery and hash lookup. So these modules scan the raw sectors of the drive to find those hidden data clusters. And it worked. So if you look at the bottom screenshot, Autopsy found the artifacts. They are marked with that little red X, which tells us they were indeed deleted files. So from here, I just had to extract them to a secure folder so we could verify if they were still intact. Finally, the most important part is the comparison. So I checked the recovered files side by side with our original baseline. So if you can see, the file name and size were 100% match. So we know the data integrity is perfect. Now you might notice the timestamps, the created and modified dates actually changed to the recovery date. So just to be clear, this is totally normal because when you export a file from Autopsy, Windows treat it as a new file on your computer and it gives it a fresh timestamp. But because the file size and content didn't change at all, we can confidently say the evidence was not altered. And that's a wrap for task 1.
Now, I will explain the forensic investigation life cycle. First is identification, where we recognize the USB thumb drive as a potential source of digital evidence. At this stage, we record important details like storage, capacity, and device type. Next is as acquisition. Instead of working on the original device, we create bit-by-bit forensic image. This ensures all data is preserved, including deleted files and hidden space. Then come analysis, where tools like AutoSpy are used to examine the image. We can recover deleted file and review metadata such as timestamp and file activity. After the that is documentation. Every step, tools, and result must be recorded carefully to ensure the investigation is transparent and repeatable. Finally, reporting, where all findings are summarized into a structured forensic report. This life cycle ensures the investigation is systematic, accurate, and legally reliable. Next is evidence handling and chain of custody. Chain of custody is very important because it tracks who collect, handle, and store the evidence from the start to finish. This ensures the evidence is trustworthy in court. In our simulation, the USB drive was labeled with a unique identifier as physical evidence. A chain of custody form was filled, including details like date, time, investigated name, and store location. Importantly, the original USB was never accessed directly. All analysis was done on a forensic copy to avoid altering the evidence. We also log all auto-spy sessions with timestamp and store output in a secure access control location without proper chain of custody. Even valid digital evidence can be rejected in court. So handling evidence correctly is just as important as analyzing it. Last but not least, I will explain the recovery, success, and data integrity analysis. In this investigation, we achieved 100% coverage, meaning all deleted files were successfully recovered using AutoSpy. To verify integrity, we use hash function like MD5 and SHA1. These generate unique digital fingerprint for files. We compare the hash value of the original and recover file, and all value match. This confirms that no data was altered or corrupted. One key observation is that when files are deleted, only the directory entry is removed. The, the actual data remain until it is overwritten. This is why tools like AutoSpy can recover deleted file from unallocated space. However, if secure wiping methods are used, such as DoD 5220.22M, recovery would not be possible. Overall, this proves that data integrity was maintained and recovery process was successful.
Now, we will transition to second core area of our project, data acquisition and hashing within a Linux environment. Our primary goal here was to simulate a professional forensic workstation setup. We focus on four key objectives: establishing a virtual box VM, visualizing forensic tools like DC3DD and Mega, creating redundant disk images, and finally using MD5 and SHA1 hashing to mathematically prove the integrity of our evidence. Next, to ensure an isolated and controlled environment, we installed Oracle VirtualBox on the host machine. The virtual machine was configured with 4 GB of RAM and a 50 GB hard drive to handle forensic images. After downloading the official ISO from kali.org, we completed a graphical installation and performed a full system update using the ft update and upgrade commands to ensure all forensic libraries were current. For acquisition phase, we initialized two powerful tools. First, DC3DD, which is a command line tool specifically enhanced for forensic with features like auto hashing and error logging. Second, we use Mega, a graphical forensic imager that supports various formats, including expert witness format and raw DD. Both tools were tested to confirm they were ready for formal acquisition. Next, in digital forensic, documenting the operating environment is critical for the chain of custody. Before touching the evidence, we executed a series of baseline commands. We used date to record the exact start time, uname A to document the specific kernel version, and whoami to verify the user privilege under which the acquisition was performed. So next, we identify our 2 GB evidence drive as dev SDB. For the primary image, we use DC3DD command that compute MD5 and SHA1 hashes simultaneously during the imaging process to save time and ensure accuracy. We then repeated the process using GUI to create a secondary image, providing us with two independent copies for verification. So next, you might ask, why create two images? The answer is redundancy. By generating both primary and secondary image in raw DD format, we can cross validate them. In both images produce identical hash values, we have mathematically proved that they are exact unaltered copy of the original evidence drive. Next, this slide shows our verification results. Using the MD5 sum and SHA1 sum commands, we compare the hashes of our forensic images against the source drive. As you can see from the logs, the value match perfectly. This confirms that our acquisition was successful and that the evidence is forensically sound and ready for analysis. Next, to safely examine the contents, we created an isolated mount point and mounted the primary image as read-only. This is mandatory step to prevent accidental data spoilation. Upon listing the contents, we rebuilt the hidden directory structure and successfully recovered an image file named EFTA 00003290.png, proving our acquisition was 100% intact. So, in conclusion, our work across both Auto PSY and Kali Linux highlighted three vital lessons. First, structured procedures are essential for evidence admissibility. Second, hash verification is the only way to mathematically prove data integrity. And finally, maintaining a strict chain of custody and using read-only analysis are non-negotiable best practices in the field of digital forensic. Finally, here are the academic and technical resources, including NIST guidelines and official tool documentation that inform our methodologies and ensure our investigation follow industry standard. Thank you.